We left off last time in the discussion of Huffman codes right after this proof of optimality. Maybe to do a very brief recap, Huffman codes were constructed with this algorithm. You so it's a character encoding. It assigns a single code word for each character, but the code words can be of different length, unlike the very simple fixed length encodings that we first looked at. Now, how do we find a Huffman code? We select two characters in the alphabet that currently have the lowest weight, so that occur the least frequent in the text. And then we combine those two into a single super character representing the pair of the two. And in terms of the code words, this will mean that the two characters are essentially distinguished by the last bit, and they share a certain prefix in the code words that is yet to be determined. Now the algorithm proceeds by combining those into this new character with the sum of their weights, and then you recurse. So you apply the same strategy, which means jumping back to step one, finding the next two smallest. And here we had a small example where we found one after each other these characters. I decided to put an example on this also in tutorial 8 that will come up. It's not yet on the website, but you will get your chance to practice this. The result of this process is the Huffman tree, and the Huffman code is formed by, say, for example, the character O, following the path from the root to this leaf that there you find 0, 0, 1, and that gives you the code word for this letter O. So much for the recap. When you apply this, make sure you apply the tie-breaking rules. All right, we proved last time this theorem, but I was a bit quick, so maybe I also recap that proof very briefly. The statement was, whenever I have an alphabet with weights on the characters, then this algorithm I just sketched, Huffman's algorithm, computes actually a code that has the minimal expected code word length. So a code that minimizes this quantity E of L, which is the length of the code weighted by the weight for this character. That's all it is. And in the application of coding a specific text, this is the size of the coded text. So it's an optimal code in this sense. And the proof went along these lines. Whenever we have any code trie, we can keep the shape of the trie and swap the letters in the leaves around. So maybe if we go back to this trie, I can replace this by a different code, but of the same shape. So this is the shape. This tree has this shape, and there's 4 leaves that I can stick characters in, and I can decide whether I want to leave this order as we had it, or I can also swap it around. As long as all the characters are still present, this is another valid code trie, but in general it will not be a Huffman code, because if you compare the length of this code, it will be worse than this one. There's this character S, which is very frequent, but now I assigned S a very long code word. But still I can do this. This is never an invalid trie. So that's the first argument here. Whenever I have a trie, I can keep the shape, swap the letters in the leaves around. That leaves me with another valid code. Now, if I started with an optimal code, swapping characters around should only make the code worse. It can never make it better. But at the same time, putting 2 lowest weight characters in the deepest leaves in the trees can only make the tree better. If originally these lowest weight characters were somewhere else, I could swap them to those deepest leaves. And if the original code was optimal, then actually this leaf where they came from must have been at the same depth. Otherwise we would have well, strictly made the optimal code better. So that's not possible. All right, that means we can always put the two lowest weight leaves in those two lowest hanging leaves, and that was what the algorithm enforced by grouping them as one character, and that's why we can always find an optimal code tree that has the shape of these Huffman trees, and that's why the Huffman's algorithm computes an optimal length code. There's another way to measure how good Huffman codes are, and that has to do with a concept that's also used in other contexts, especially in physics. It's called entropy. Now, if you come from physics and you've heard entropy in the thermodynamic sense, it is related, but it's distinctly different. So for the moment, forget your knowledge about physics and just focus on this definition. It's a simple mathematical definition. If you're given probabilities, so some numbers between 0 and 1, and their sum has to be 1, then you can define an entropy of this distribution by just summing up these terms, or the more intuitive one is this one. Now, entropy is a little abstract, but for this module, it's enough to say it's a measure of the amount of information that is given by a random variable that follows this distribution. Or in the coding sense, it's the expected number of bits that I need to nail down or to encode the outcome of a random experiment where the different outcomes have these probabilities. So a simple example maybe, let's take a fair die. So it has the outcomes 1, 2, up to 6, and they all have probability 1 over 6. Then if you compute the entropy, if you insert this into this formula, you actually get that these are, well, the terms are all the same, so the sum is just 6 times. Then we've summed up this, so it's 1 over 6 times log of 1 over 6 is just 6 again. So that comes down to log of 6. Which, well, whatever it is, if you have a calculator handy, you can check it out, but it's something between 0 and 2 and 3. 2 point something. So that means if you roll a fair die and you want to communicate to someone the outcome, then you need 2 point something bits on average to do that. Now, this is a bit of a problem. If the entropy is not an integer, how can I use 1.5 bits? I cannot in the strict sense, but on average I might, because there might be, in my case here, what would be the Huffman code for this? Maybe let's do this quick example. So we have 1 and 2. I'm constructing the Huffman tree or the Huffman code for these symbols 1 up to 6. I would continue grouping these because the lowest weight is always the individual symbols, but now I would start grouping those together. And so shape-wise, the tree would look like this. Now I violated the tie-breaking rules. So this is not the expected outcome I would like you to have for the tree. I would want that this is on the other side, but I can edit the trees. So this is something you can't do nicely on the paper, but I can do it. Oops. The problem is that the type-breaking rule says that the smaller tree should be on the left. So we can do this. Now that would be the Huffman code. And that would mean we spend 3 bits. These are all at depth 3. We spend 3 bits for the numbers 1, 2, 3, and 4, but only 2 bits for the numbers 5 and 6. So on average, we do spend here 2/3 times 3 bits plus 1/3 times 2 bits. That is something non-integral. It's 2 and 2/3. So it's not a problem that the entropy is a number. It's not necessarily integral. It's possible that also a Huffman code gives you a non-integral average number. So if you take the average over all the leaves in this case. Now here it was fairly easy to construct the tree and to compute entropy because I assumed a fair die where all the 6 sides have the same probability. The entropy tells you what happens if someone cheated, if someone fiddled with this die and made one of the sides more likely to be the outcome than others. Then this amount would go down. And the reason why it would go down is that as soon as you make some outcome more likely, you're less surprised to see this outcome. If you assume you know that this die has been tampered with and it shows 6 almost all the time, if you see another 6, that's not very surprising. So you would assign a short code to encode the 6 if that die had been tampered with. You can also interpret this term directly. So if you look at this term, it's actually an expected value. You take something and multiply it with its probability and sum this up over all possible outcomes. That's an expected value. And in this case, it's the expected amount of bits you need to encode. But with a hypothetical code that spends exactly log of 1 over pi bits to encode the value I. And the entropy says that this is the best you could do. If you manage to get exactly this, your code will be optimal. But in general, you cannot. So if this is a non-integral number, that means the depth of the leaf in the tree would be not an integer, and that cannot work. All right. There's a formal connection to Huffman codes, and that's why I talk about entropy for this module. Whenever you have a Huffman code and you have its length of the code, so the quality of the code, the expected length of encoding one symbol, you can bound it by the entropy. It can never be better than the entropy. The entropy is a lower bound for any type of code. But you can also put an upper bound on this. So you can say this E of L is really between h and h plus 1. And that's very useful in estimating how helpful a Huffman code is. And it also shows you that even though you sometimes have to round when this is not an integer, you never have to round very often. So that's what gives you a statement about the quality of Huffman codes in general. So to see how well you understood this entropy things, here's a question. So h is exactly the entropy as we defined it here, and sigma is the size of the alphabet. I'll start the question in a second. As we had it usually. All right, there you go. And as always, if you have any questions or any issues, let me know via the live chat. All right, to give you a little more time, because people reported that today it seemed to be a little lagging behind for some of you. I can start the attendance recording question at the end again. So one thing I didn't say, but well, maybe something to discuss once you're done voting. You might notice that a lot of these points include the log of the size of the alphabet, and you might wonder why that's an interesting quantity to compare with. I'm not sure how frequently my chat is updating, so if you want, you can tell me if you're done. Okay, 4 seconds anyways. All right, so a majority voted for whenever h is less than log sigma. I would say, so I said this is correct, but really because I had to select one. In some sense, there's several answers that make sense, and even answer C is not quite incorrect. First of all, compared to a fixed length encoding, a Huffman code is always the optimal way to encode the characters of this alphabet with the given weights. So no matter what you do, you will never be worse off by using the Huffman code. But if you want to read this very strict, more efficient could mean strictly more efficient. And in that case, the Huffman code could just be as good as a fixed length encoding. Now, if you have this condition D, if h is smaller than this, remember that the Huffman code, that was the upper bound we just had, is always at most h plus 1. So if h again is less than this, this would be less than log sigma. And log sigma is the number of bits you would need in the best case. If you don't round, you would really have rounded up here. Log sigma is what you would have in a fixed length code. If sigma happens to be a power of 2, you could actually realize the log sigma. And in that case, and only in that case, you can achieve this. Now, if this condition is true, that says the length of your Huffman code is strictly better than whatever you could achieve with the fixed length code. If you only have this, for C, you would only get that this is less than log sigma plus 1 from the same argument. And so you can't really say much. It might be that the Huffman code is actually the same as the fixed length encoding. All right, that was just to practice a little bit the definitions. One thing I wanted to add here is the entropy is always at most log of n in this notation. If you have n different outcomes and you sum these things up, the entropy is at most log of n. That was what we had with the die example too. So it's maximal if all the pi's are the same, and then it has this maximal value, and that was the one that I compared with here. All right, so Huffman codes work fairly well. Now, last time I didn't go into great detail how to actually encode a given text. I was assuming we already have the alphabet with all the weights given. So the overall procedure would be as follows. You make a first pass through your source text S and determine which characters occur and how often. The second step is what we've seen above. So this is really the procedure of building these trees. And that would construct the code for the given character frequencies that we just determined. That would determine this optimal character encoding. The next step is, because the code depends on the source text, we can't really decode well, without knowing the source text. But that's a problem, because we want to decode the source text from the coded text. What that means is we have to store the Huffman code itself as part of the coded text. We have to somehow tell the decoder, look, this is the code words for the letters that I will use for the rest of the source text. I won't tell you in detail how this is done. There's many options and there's many opportunities for further tricks there, but if the text is long enough and the alphabet is not too big, the details don't matter so much. So that's why we don't discuss that in detail. And then the second pass is actually storing the source text using our code. So you go through the source text and each character is encoded using E, and you append the code word to the output, to the bit stream that encodes your source. Decoding just does the same thing in reverse. You start reading the Huffman code from E. Again, the details are omitted, but what that step has to do is to reconstruct this Huffman trie. And then the second step is you read character by character from the coded text and decode it using the trie. So again, remember, if you have this trie with the different leaves, each bit in the input tells you whether you go left or right. So there's the 0 and the 1 in each step. And that, when you reach a leaf, tells you what to write to the output. And then you continue back at the root. A remark here is that Huffman codes are an asymmetric scheme in the sense that decoding is simpler than the encoding, because we didn't have to do this separate phase and we didn't have to construct the code. We do have to read the code from its encoding, but that's an easier task. And then we only need a single pass over the much longer coded text. Whereas here, without further tricks, we cannot avoid going through the text twice. We didn't talk much about the running time, but I mentioned that you can implement the phase of building the tree, the Huffman tree, with a priority queue. So we have to initialize this priority queue, and then for every character in the alphabet, maybe except the last one, we delete the 2 mins, and we also insert this new pair character. So that gives us this running time. Now, if you remember what the running time for the priority queue operations was, that's essentially logarithmic in the size of the queue. So that gives you this sigma log sigma. If the characters happen to be sorted by weight, there's actually a nice trick that you can speed this up to a linear algorithm using 2 queues, but we won't cover the details here. And then the time for the encoding, for the actual coding of the source text, once you've constructed the Huffman code, is linear in the size of the text and the size of the code, because you have to write that down too. In practical applications, Huffman coding is part of the fundamental tool set in many compression methods and many tools that are out there. It's typically not used in isolation in the way I presented you, but it's part of a larger pipeline. And there's a couple of variations where people tweak the details to make it slightly more efficient. To sum up on Huffman codes, we found an optimal solution for this nice, elegant subproblem where we want a character encoding. So given fixed character weights, we can optimally solve this problem, something that at first sight might have looked like it's impossible even to do efficiently, but it's efficient, even essentially linear, almost linear, like sorting. The decoding is very fast, and the encoding, the code that we get from this, is robust in the sense that if we locally flip a bit from 0 to 1 or 1 to 0, that will of course corrupt one or two symbols in the local proximity, but it will not get the whole code out of sync. And we'll see later examples in this unit where this actually happens. So this is a plus. The downside is that one downside is that it needs 2 passes over the source text, as I just mentioned. And the second is that we have to store this code alongside with the coded text, which means even though the actual Huffman code is optimal, this could still lead to an inflation of the total size because you have to store this code alongside the text. If the original encoding of the text was already close to optimal, you're actually making things worse by insisting to first writing down a code and then using it, but it actually didn't really help. So that's one of the dangers or one of the downsides of Huffman coding. There's the chance to make things worse. But that concludes the discussion of Huffman's coding, definitely a fundamental toolbar part, fundamental item of the toolbox for compression.